Hello everyone, welcome to SYNTHFOX channel. This is Obrilis, and today I will be presenting you my new module called the Shift Chord Generator. It is a quasiquencing powerhouse that can produce a wide array of stepped voltages and gate signals, ranging from looping 16-step patterns to more complex phrases to full-on random insanity. As the name implies, at the core of the module is a 16-bit shift register. The two inputs of the shift register are the clock input and the data input. The three groups of outputs are derived from and deterministically depend on the shift register contents, the 16 bits each taking one of the two states, 0 or 1. Although the shift chord generator is a very complex module on the inside, it's very easy to get started with. The only thing you really need is some kind of a clock source. Any signal will do, as the clock input is fit with a comparator. So, we could use, for example, 2CK, a conventional clock generator, or we could use an LFO produced by looping con. That's what we're gonna do. Take the con output and pass it to the in jack on the clock input section. No activity just yet, because the threshold knob is set all the way up. Let's tune it so that we start getting a pulse. The comparator extracts pulses from any kind of signals, and this pulse is further available at the output jack, fit with an indicating LED. As you can see, some activity started happening across the shift chord generator. The LEDs started blinking all around. Now let's try using the shift chord generator's outputs in a very simple demo patch. We have a simple VCO to a VCF to the output mixer patch going on here. Let's use the 4-state output to control the oscillator pitch. As you can see, it started moving in octaves. Now let's use the 16-state output to control the filter cutoff frequency. Quite instantly, we had two-step voltages controlling the frequency of the oscillator and the filter. Now let's use the 128-state output instead of the 4-state to control the VCO frequency. In an instant, we get a more atonal and complex soundscape. Now that I showed you how to quickly get started, I will overview the module in more detail. Before we jump to exploring the shift chord generator, I will give a brief theoretical explanation of what's going on at the module's core. A shift register is a special device containing binary information. The analog content processors use the 16 bits of the register to derive the module's output signals. The shift register is controlled by the two input signals, clock and data. More in-depth explanation on inputs and outputs of the module will follow, but for now, let's look at this more generalized case. Every time you turn on the device, the contents of the register will be random. They are updated as the clock transitions from 0 to 1 in the following way. First, all the bits on the register are shifted, hence the name. After that, the last bit, the rightmost on this drawing, gets thrown away and forgotten. An empty place on the left then copies the state of the data input at the moment of the clock transition, 0 or 1. Here, the data input was 0, so 0 got written to the first bit. The shift register now presents an altered sequence of 1s and 0s. The content processor's complexity further amplifies this difference, and the module's output voltages change. This all happens instantly the moment the clock transitions from 0 to 1. To trigger the next change, the clock first has to transition back to 0. Suppose that in the meantime the data input became a 1. This does no change to the shift register, as it only updates when the clock input goes from 0 to 1. When it does, the same routine as before happens. This way, the contents of the register get updated, and the output signals change. The order of 1s and 0s in the register, as well as how many more 1s there are than 0s, directly and deterministically define the output signals of the module. As I already mentioned before, the module's name, Shift Core Register, implies that there is a shift register as the core of the module. The contents of the shift register, the 16 bits, define all the outputs of the module. The shift register is controlled with the clock input and the data input, each having a dedicated subsection in the module. Both the clock and the data input have dedicated comparators, so any signal can be used as the clock or data source. While using a dedicated clock or gate source like the 2CK makes sense, shift chord generator has been designed to be used creatively with modulation sources like con, audio signals, noises, and any other kind of signals you may find in a Eurorack system. Both the data and the clock input comparators can be adjusted, so let's look into that. Here I'm taking the output of a looping con set up as a triangle LFO signal. I patch it to the in jack on the clock input section. As you can see, the LED is showing some activity. The pink knob and its dedicated TCV input define the comparator's threshold voltage. Above this voltage, the input signal will be treated as 1, while if it falls below the threshold voltage, it is treated as 0. It is possible to dial in such a high or low threshold that the signal used as a clock source never reaches it, essentially halting the module. Otherwise, this threshold can be controlled manually or externally to define which part of the signal is treated as 1 and which is treated as 0, allowing for extraction of more precise pulse information from the clock source signal. The result of the comparison is indicated by the LED of the clock input section and is also available at the jack labeled out for daisy chain synchronization of other sequencers and such. Each time the clock input section LED lights up, new data is written to the shift register. But what exactly is written to the shift register is defined by the data input section. Just like on the clock input section, the data input section has manual threshold control of the comparator. It as well has voltage control over this threshold. However, unlike on the clock input section, the data input section TCV input has a dedicated attenuverter for more precise modulation control. The data source is input to the in jack at the very right of the section. This comparator part of the data input section works exactly the same as the clock input comparator, except for the attenuverted TCV input. The module features an onboard noise generator, and its output is available at the data input section at the NOI jack. This noise can further be used in any way you like. The most common usage for it would be an audio source or a sample hold source. This noise source output is also normal to the data input jack if the switch is in the upper or NOI position. However, if the switch is in the lower or self position, the last bit of the shift register is normal to the in jack, thus cycling the shift register on itself and creating a looping 16-step pattern. Now that I explained how to control the shift core, let's explore the outputs it produces. The end state outputs, the binary outputs, and the stepped CV programmer are the three groups of the outputs of the shift core generator. For a quick start, let's set the data normaling switch to NOI position, set the data threshold to exactly noon, and provide a clock source to the module. I will be using 1/2 of the 2CK. A dummy cable is connected to CV inputs of both halves of the 2CK to break the cross-modulation that occurs if nothing is patched in. The clock input detects the pulse nicely and we can see some action happening. If it's not detecting your clock source correctly, please adjust the clock input threshold knob. I set up a simple VCO to VCF to the output mixer patch like before for simple demonstration, and we will begin with the end state outputs. Each of the end state outputs is labeled with a number. This is the number of quantized states that this output may take. The number of states varies greatly, from 4 all the way up to 128. The end state outputs directly use the shift register contents to derive stepped signals. The more ones the shift register has, the higher will all the output's voltages get. Here, I am using the 4 output to control the VCO pitch. The 4 and 8 state outputs change in equally spaced quantized voltage steps. The 4 state out is tuned to produce octaves, while 8 produces fifths when connected to a 1 volt per octave VCO or such. The outputs in the lower row do not have equally spaced states, however, they have many more possible states, 16 to 128, producing more complex and less tonal step modulation signals. I'm using the 8-state output to control the VCO pitch and the 16-state output to control the filter frequency. While all these n-state outputs use the contents of the same shift register, and generally, the more ones you have in it, the higher the outputs will get, and vice versa. The relation between the outputs is not obvious at all. While one output may shift up, the others may as well shift down, shift up, or stay the same. Here I will use the 128-state output to control the VCO pitch instead of the 8-state output. As you see, we're getting a much more complex and atonal picture. Gets somewhat less complex if I use the 32-state output. The binary output section at the bottom left of the module produces binary signals, or gates, as a result of complex processing of the shift register contents. Perfect for timing the musical events in the system, triggering drums and function generators, gating envelopes, clocking sequencers, and so on. Here they are triggering the degenerator set up as a drum module. The third output section is the stepped CV programmer. This is a shift chord generator style approach to more standard sequencing techniques. Like the binary outputs, it derives 4 new signals by processing the register contents. Those are then sent to the knobs labeled alpha, beta, gamma, and delta. The LED next to each knob indicates if the knob is active, and if it is, the knob defines how much it contributes to the final mix available at the out jack. The update clock input jack labeled UPD triggers the update of the 4 signals used by the programmer. The clock input section's out is normal to it, so it updates in sync with everything else if nothing is patched in. Yet, it is possible to run this section asynchronously from the rest of the module. When active, as indicated by the LED, the knob creates an offset at the output. The more clockwise the knob, the bigger is the offset. In various combinations, the 4 offsets make the VCO play one of the up to 16 notes. Right now, only the alpha and beta knobs are dialed in to have some effect. Thus, we're getting 4 different tones. For more musical complexity, we can add in more offsets with gamma and delta knobs. Now I will use the B half of the 2CK as a separate clock for the stepped CV programmer. You can see now it runs at lower speed than the rest of the module. This can be used to make more rhythmically complex patterns while using it along with the other outputs of the module. For an even more complex soundscape, I will pull off the cable from the 2CK, thus enabling the cross-modulation to happen. So far, I've shown how the inputs work and explained the many outputs of the shift chord generator. However, I yet have to speak of quasiquencing, the quasi-sequencing methods of controlling this device. For this, I set up a patch where the binary outputs are used to trigger some samples on the degenerator, while the 2 n-state outputs modulate its pitch and character. Let's bring the degenerator's sound up on the mixer and hear what's going on. Right now, the switch is in the noise position, so noise is normal to the data input. Since noise is purely random, one cannot predict precisely if it's going to be treated as 1 or 0 at a given moment. However, we can affect the chances by raising the threshold and getting more zeros on average, or lowering it and getting more 1s. This way, one can affect how intensive are the changes in the register, as well as the proportion of 1s and 0s inside of it. If the threshold is too high or too low and the register is being filled up with only 0s or only 1s, no change occurs. The most intensive and uniform change is with the threshold at noon. From this rather chaotic mode of operation, it's easy to switch into an orderly 16-step pattern by simply setting the switch to self mode. Putting the switch to the upper NOI position for a while and then setting it back to the self position yields a new pattern. So far, we've only been using the switch and the normal connection to the data in jack, using either noise or the last bit of the shift register itself as the data source for chaos and order respectively. However, there are many external data sources of complexity between noise and self that may produce sequences of different complexity levels. This is what we call quasiquencing. In this example, I will use the other half of the 2ck running on its own as the data source. Although 2ck produces a binary signal and we cannot play around with it using the data threshold, the relation of its speed related to the clock speed is what defines the emerging pattern. While not dialing in the pattern directly, you have full deterministic control of it via controls of the data source and the data input section of the module. This is the nature of quasiquencing. Another option is to use a more interesting signal as the data source. I will use the slow triangle LFO produced by Con. Since it's a continuous analog signal, paying attention to the data threshold makes sense now. Now it defines the character of the pattern separately from the data source signal. The emerging pattern, of course, can also be easily controlled via the attenuverted TCV input. In this example, I made a way more complicated patch using the same techniques as mentioned before. I'm using one half of the 2ck as the clock source and the other as the data source. The difference of speed between the two halves of the 2ck is what defines the pattern now. However, since the patch got so complex, and many aspects of it are now controlled by the shift chord generator, the changes may be very drastic. Since the switch on the data input section of the shift chord generator is set to self mode, we can easily switch the module to 16-step pattern operation by simply plugging out the cable that goes to the data in. Up to this point, I've only been showcasing the shift chord generator as a tool for stepped control voltages and gates. However, this module is a great sound processing tool as well. Doepfer VCO's triangle output as the clock source. Since the clock input of the shift chord generator is fit with a comparator, it can accept any kind of a signal, sound included. Adjust the clock input threshold so that some action starts happening, and we're ready to go. Let's put one of the end state outputs to the mixer and hear it. Since nothing is patched into the data in jack and the switch is in the NOI position, noise gets normal to the data in and eventually gets, so to say, digitized at a rate set by the clock source, the oscillator in our case. Using the data threshold knob, we can define how much activity is happening. In other words, how big of a sound are we getting. This, of course, is voltage controllable, so I can use some control voltage to control this volume of the noise. Created with Con is now controlling the percepted volume of the noisy sound. This may get even more interesting by using another sound as the data source, and then using some feedback between the shift chord generator and the sound sources to further enhance the texture. I will use the filter set to resonate. Let's check how it resonates first, and then I will patch it to the shift chord generator's data input. Playing around with the clock input and data input thresholds may change the texture up to stopping it completely. The real madness begins when you start feeding back the signals from the shift chord generator to the sound sources. In this situation, I will put the step CV programmer output back to the VCO 1V per octave input. Now the alpha, beta, gamma and delta knobs of the step CV programmer are additional controls to the texture. We can further improve this feedback interaction. Since one of the sound sources is a filter, we can use one of the shift chord generator's gate outputs as a sound input to the filter. Thank you for your time today. I'm going to let you off with another patch, which I am furiously explaining in the video. Sadly, the video turned out really long, and it's better to not include the full explanation. This patch is similar to classic Krell patches, with shift chord generator in random mode and looping con as its main drivers. Thanks to the quasiquencing capabilities, shift chord generator goes from full randomness to 16-step loops and all the complex phrases in between with ease. So, it easily becomes the core element of any system and any musical piece, from orderly techno to insane noise walls. For more information on the shift chord generator, please check the links in the video description. If you don't want to miss out on further updates and new videos, please subscribe to this channel and turn on the notifications. Thank you for watching this video. I've been Aubrey Liss of SYNTHFOX. Till next time! Wow.